Did you ever write
What do you mean? Yeah, I wrote one. When I was doing the loop stuff, I wrote one.
Oh, really? Where should it go?
Oh, it's not checked in. I just wrote it.
Yeah.
I'm not. I don't know. Do you want to check in there?
Yeah, I have to check on it.
I want on this page and say, why should I want Bitcoins? How can I get Bitcoins? Why do I want I'm a local trader.
Testing.
Oh, Bitcoin traders. Carl. It's just a different name. Carl.
They should be famous.
They are famous. They're not even famous.
Or later.
Brad. Oh, he's got a kid. Unless that's Brad. In which case he has a father. He's got massive Bitcoin. No, I'm excited about this. Brown bag. Any brown bag of that. You know, some dork from MIT. Chicago? No, I studied in Rhode Island, like near Boston, on the East Coast. But this is my first time on the West Coast.
Really?
Everybody says so much about it. You know, you hear it's all yeah, it's all true, like sunny all the time. Warm, I mean, everybody's all cheerful. Have you been here?
We'll give it one more minute to show up.
I came to the West, so I'm studying here. But I came to a bunch of schools.
Oh, yeah?
So I visited a bunch of schools that I worked at.
What school do you go to?
Berkeley.
Okay. How much Berkeley like? Yeah.
I have no idea. Because it's moving homes. Blake is Guildford is very happy in the morning. When you say no one's here, do you hear or do you not?
I went to like friends' house. So I didn't actually get to see much, but
Some good things happen.
yeah.
All right, we good with video?
Why they shouldn't have that?
Very good. All right, let's get started. Hi, everybody. Thanks for coming out. I'm going to be talking about Bitcoin today. It's an interesting kind of digital currency system that's been making the news the last couple of months. I'm going to be doing a kind of technical deep dive on the protocol since there's not a lot of kind of accessible documentation out there about how it actually works. There's a lot of discussion about what it is and how people use it and the consequences, but not so much on the internals that I've seen so far. Slides are available up there on people if you want to follow along and see the stuff for yourself. Okay, first off, what is Bitcoin? There's a nice, simple 90-second video here that will capture it better than I can. So I'll just play that for you.
What is Bitcoin? Bitcoin is the first decentralized digital currency. Bitcoins are digital coins you can send through the internet. Compared to other alternatives, Bitcoins have a number of advantages. Bitcoins are transferred directly from person to person via the net without going through a bank or clearinghouse. This means that the fees are much lower, you can use them in every country, your account cannot be frozen, and there are no prerequisites or arbitrary limits. Let's look at how it works. Bitcoins are generated all over the internet by anybody running a free application called a Bitcoin miner. Mining requires a certain amount of work for each block of coins. This amount is automatically adjusted by the network such that Bitcoins are always created at a predictable and limited rate. Your Bitcoins are stored in your digital wallet, which might look familiar if you use online banking. When you transfer Bitcoins, an electronic signature is added. After a few minutes, the transaction is verified by a miner and permanently and anonymously stored in the network. The Bitcoin software is completely open source, and anybody can review the code. Bitcoin is changing finance the same way the web changed publishing. When everyone has access to a global market, great ideas flourish. Let's look at some examples of how Bitcoins are already used today. You can purchase video games, gifts, books, servers, and alpaca socks. Several currency exchanges exist where you can trade your Bitcoins for dollars, euros, and more. Bitcoins are a great way for small businesses and freelancers to get noticed. It doesn't cost anything to start accepting them, there are no chargebacks or fees, and you'll get additional business from the Bitcoin economy. For your first Bitcoins and more information, visit weusecoins.com.
Yeah, alpaca socks. We also got Bitcoin nerd badges. It's a commodity. Commodities are things that are fungible, they're transferable, they're somewhat scarce. Digital ones are ones that can be transferred electronically. So the most common examples of this everybody's familiar with is World of Warcraft Gold, Second Life, Lynda dollars, stuff like that. Decentralization means that there's no single party that controls the creation, allocation, or transfer of this commodity. Unlike dollars in World of Warcraft Gold, there's no board or a company that decides when to create more. And you're not dependent. You're dependent upon a central party in centralized systems. We want something different now. From the operational point of view, every user has a local agent called BitcoinD. There's an API to that. There's a little GUI that drives it. That agent manages a protocol, holds all the Bitcoins, all the keys that drive those. Those agents talk to each other over an overlay network off the internet, and they manage the transfer of value when you tell it to transfer value. Users send payments to each other by giving an address and value to a local agent. You hit send. All the addresses are cryptographic identifiers of public keys, signing keys. The agents send signed messages to each other in order to transfer the coins around. And the receiving user's agent gets the message, checks all the signatures, and informs the recipient that they've just been given some money. So what is wrong with decentralized currency? Why do people want to bother doing something more decentralized? From a security point of view, we'd like the usual properties of a currency, like unforgeability and theft-proof, protection against theft, to be enforced by code and by math, rather than upon behavior and the goodwill of the participants. World of Warcraft Gold is something that you depend upon the company to not take it from you arbitrarily or not transfer you guys off to somebody else. And it'd be nice if we didn't have to rely upon people's behavior for that. From an economic point of view, there are a lot of folks that would like the total money supply to be predictable. They're a little bit irked that there's a Federal Reserve Board that can add new money into the system anytime they want, because they can't predict when they're going to do that. And that affects your ability to kind of anticipate what inflation is going to be like, what the expansion of the money supply will be like. So they'd like something that's a bit more concrete, a bit more predictable, and again, not dependent upon people's behavior. Putting a lot of power into one place is kind of an invitation to abuse. If you have all of the keys, all of the money in a single bank, then people are interested in robbing the bank. There's a big financial incentive for doing it. If you can spread that power out among multiple users, then there's less of an incentive to go and try and take it over. And so that helps security in a lot of ways. The most important thing that a currency can do is to inspire confidence among its users. It's something you're willing to give up things that you do value in order to trade it, to exchange it for other things of value. So Bitcoin is kind of an experiment. It's testing a theory that more users will be willing to accept a decentralized currency over one in which they have to trust a single person or a single government or a single company. So it's an interesting experiment to see if this kind of stuff works. When we are specifying a new money system, we need to define a couple of different things. We need to explain how it's represented, how it gets transferred from one party to another, and how it gets created in the first place. Scarcity is an interesting and important property of a currency, of a commodity, but there has to be more than zero of it in order to actually have something to transfer around. So we have to, in our definition, we have to explain how it gets created and kind of at what rate the money supply expands. You can imagine lots of different curves for how much money appears over time. That's a policy decision. When you add new money into the system, it helps whoever gets the new money, whoever's the recipient of this new bonus. It hurts everybody else just a little bit. Everybody else's value gets a little bit less. There's a bit of inflation triggered by that. And it's necessary, at least initially. So it's something you have to manage. You have to kind of trade off these pros and cons of it. Okay, so if you're familiar with digital money systems, they roughly fall into two different categories. There are discrete coin systems that are kind of the more classical, cypherpunk currency systems. Chom's DigiCash system is kind of a classic example of this. In these systems, the bank issues a lot of coins with a very small number of denominations. The coins are blinded. The bank can recognize its own coins later, but it can't tell which one is which. And so you give the coin to somebody, they give the coin to somebody else, they redeem it for the bank. The bank can tell this is a real one credit coin, but I don't know which one it is, and that's where you get the money. The other kind of system is a ledger system, in which there's a balance sheet, and the bank is tracking a balance for each user, and every time there's a transfer, they increment one column, they decrement the other one. A really good example of this is the way that any large game, World of Warcraft, Gold, good example, Facebook credits, kind of classic, we'll just remember how much your balance is and tell you about it later. Despite having coin in the name, Bitcoin is a bit more like a ledger system than like a coin system. So I'm going to try and explain how Bitcoin works by starting with the kind of classic ledger system and evolving it one small step at a time into something that explains how Bitcoin works. So imagine you're a programmer at the newest, hottest online game, and you've been given the job of creating a money system for this thing. You'd probably start with a database, because everybody loves SQL. Every user gets an account. There's a balance in there. The system has to handle transactions that move money from one account to another, transactions that create new money, new currency in here. Maybe somebody bought it with dollars. Maybe they raided a dungeon and they found gold in a chest somewhere. And also transactions that destroy money, where you're extracting it out of the system. Either you redeem your Second Life Linden dollars and they send you a check, or you buy a Vorpal sword from the system. And so the total currency in the system drops by a bit in exchange for something else of value. Your system is going to maintain some invariance, like transfers from one party to another cannot create new money. The output can't be bigger than the input. No account balance can ever go below zero. You can't go into debt. You can't spend money that you don't have. So you can all imagine what the system would look like. From an authority analysis point of view, there's some piece of code that's this ledger manager that gets control over the database. And it gives out specific access, specific authority to different parties. So Alice gets access to a facet that lets her transfer money out of her account, but it doesn't let her make new money. It doesn't let her move money from anybody else's account. The bank gets a facet that lets them make new currency and assign it to somebody. So you can just kind of imagine that different parties get different control over this according to the rules of the system. So what's wrong with this kind of system? What specifically are we trying to fix? The bank has full control over the ledger. So the bank, or any attacker who manages to compromise it, gets to spend any user's money. That's a big temptation. You have to put a lot of energy into the security of that system. That's the drag. The bank can also create new money anytime it likes. So it's hard for people to predict kind of what the inflation is going to be like. They never know when the bank is going to decide, we should inject more money into the system. The only source of truth is in the bank's ledger. So users can't validate payments between themselves, and they can't even learn their current balance without talking to the bank. So it's a fully online system, and the bank is a single point of failure that the downtime of the bank prevents anybody from doing anything with it. We're kind of used to these restrictions. They're really common, but we can do better. So our starting point is the centralized ledger in which the bank has complete control. The first step that we make is that we use a public signing key, or a public verifying key to be specific, to represent each account instead of the username. Each column is associated with a very specific public verifying key. Bitcoin actually uses elliptic curve DSA for this purpose. Now, when Alice wants to transfer money over to Bob, she expresses that by making a signed message. And she signs it with the private signing key that corresponds to her column's public key. She sends that transfer message over to the bank. The bank is going to publish this entire ledger. The bank will publish all of the transfer messages it receives, and it will publish all of the resulting balances that show up in the ledger. This means that everybody out there can go and verify the signatures on each of the transfer messages. And everybody can audit the ledger, check for all of the invariants that are being maintained. They can complain about violations. So at this point, the bank's job is to collect these transfers, put them into remember the order in which they were presented, publish them out to everybody. It needs to reject underflows, make sure the invariants are maintained, and it needs to manage expansion, decide when new money should be added to the system. We're also going to, at this point, we're going to drop the ability to remove money from the system. We're going to say that the total money in the system is monotonically increasing. So that's kind of what the real world does. The government doesn't take dollars away, it just injects them. Each of these keys are actually pseudonyms, and each user can have as many keys as they want. The Bitcoin client routinely manages hundreds of keys, and elliptic curve DSA keys are 256 bits. They're really small. The overhead of that is trivial. So each user has some number of keys. And for example, Carol's current balance is equal to the sum of the balances available to all of her keys. So her client tells her that she has 27 credits at the second point in time here, even though it's actually split between two different keys. She doesn't need to pay attention to that. There are transactions that can split balances among different keys or merge them together again. And the public keys are pseudonyms. Nobody actually needs to know that A here represents Alice. This starts to help with anonymity. It's not so obvious from the outside that key A1 and key A2 are related in some way, unless you choose to announce that. All right, next step. Having the bank publish both all of the transfer messages and the resulting balances is actually redundant. You can derive the balances from a series of transaction messages. So we're going to make it only publish the transfers. And we're going to call these transactions. These are very specific kind of objects. Everybody will just derive balances when necessary. A client can pay attention to which transactions have given money to Carol and tell Carol you now have some credits. So the bank's job at this point in time is to remember the correct order of these transactions, only permit the valid ones, publish them out, and to manage expansion. The rest of the world can take on the job of validating all the signatures and making sure that these invariants are maintained and figuring out what the different balances are. So this gives us a network model in which users are sending signed transfer messages over to the bank. The bank does a little bit of checking and then broadcasts that message stream out to all users. So it's this publish-subscribe model with the transaction type that everybody pays attention to. The bank also decides to give new money out to certain people every once in a while. We still haven't explained how expansion is controlled here. But just remember there's this transaction pipe and everybody is putting messages into one end and everybody is getting messages back out. So next step, we need to enhance the transaction model a bit. We're defining a transaction that's containing some number of inputs and some number of outputs. Each transaction consumes some of the inputs and it creates some new outputs there. And each input is pointing to a previous output. This is making a graph in which some of the nodes are transactions, some of them are outputs. All of these outputs are first-order objects. We're not transferring credits from one column to another. We're really consuming an output and creating a couple of new ones. So the rule is the total value of all of the outputs can't be greater than the value of all of the inputs. That's the invariant that prevents this transaction from making new money. It's also preventing underflow here. You can't, if there is no transaction for you, no output for you to consume, then there's no new transaction with a reference. There's no way to go below zero. Each output is sent in a sense to a public key. It's labeled with the public key that must be used later to go and claim it. And so the transaction as a whole has to be signed by all of the keys for all of the inputs that it has. If this transaction is claiming to own the B1 and the B2 outputs, it has to be signed by the B2 private key and the B1 private key in order for it to be valid. Otherwise, somebody else could go in and steal that money. Somebody could claim it. The result of this is that you wind up with a directed acyclic graph of transactions and a set of unspent outputs that evolves over time. So if we imagine that we're in a starting point where there are already 3 unspent outputs sitting here from some previous transaction that we are showing here, then the first step, a basic transaction, is going to consume one of those, in this case the 12 credits available to B2 here, and produce a new one. So this is the basic transaction for Bob giving 12 credits to Carol. He makes a transaction that's assigned by the B2 key so that he's allowed to claim that input. And he produces a new output that's labeled with Carol's C1 key. So this is a simple transaction transferring 12 credits from one key to another. The old output is marked as being spent, and it's removed from the set of currently unspent outputs. Each client keeps track of which ones are currently available to be spent. A double spend is a transaction that tries to consume a previously spent output. We want to disallow these. These are invalid, and the rule is that the first transaction to come across a wire to get put into the history wins, and all of the subsequent ones are ignored. This is preventing the invariant of spending money you don't have, or this would create new money if you were to allow this sort of thing. So we need to prevent this kind of thing. And most of the rest of the protocol is actually dedicated to preventing this in a decentralized fashion. The expansion of the economy, creation of new money, is expressed by a transaction that has outputs greater than the inputs. We'll come back to this in a couple of slides to explain how exactly this happens. But just know that is how new money gets into the system. Since each of these outputs have to be consumed completely, in order to send less than the full amount of that point or that output, you have to make change. You have to send some change back to the sender. In this example, Alice is sending 10 credits to Bob, but the only output she has available is a 20 credit output, 20 credit coin. So her client makes a transaction that splits it into two pieces. She gives 10 coins off to Bob, assigning it to his B2 key, and she sends 10 coins back to herself with this new A2 key. Most Bitcoin transactions create two outputs. There's the first one transfers credit off to the real recipient, and the second one sends the remainder back to a brand new key generated by the original sender. And it just does all of this transparently. There can be multiple unspent outputs for any given key. The transactions refer specific outputs, not just the key. And a user's balance is the sum of the values of all of the unspent outputs for all of the keys they control. So at the bottom line here, Bob's balance is 66 credit because he's got a 10 credit output and a 56 knows output. Each of these transactions can create an arbitrary number of outputs, like the 3 created by this bottom transaction here. And they can consume and combine an arbitrary number of inputs. You might do this because you want to consolidate a bunch of small transactions into a big one. You might do it because you want to make a large payment and you don't have any individual coin that's big enough for this purpose. But the point is that each transaction is variable number of inputs, variable number of outputs. At each stage, the transaction log contains a certain set of unspent outputs. This set grows and shrinks over time. When consolidation happens, that set will get smaller. When you make new keys and you send your stuff out, it will get bigger. It's not strictly related to the size of the district. So what does this get us so far? What we need from the bank is an append-only ordered transaction log. We need it to be ordered so that we can resolve double spends. We can figure out, we can find which transaction came first so that we can correctly reject the second one and make sure that everybody agrees on what that is. If everybody sees this same log, then double spends and other validation failures are prevented because everybody can recognize that double spend is happening. So there's a model in which users are submitting their signed transaction to the bank. The bank is publishing a log of all of these things. A given recipient is going to check the log before delivering the goods. If you give me a transaction that claims to give me some money, I'm going to go and check the log and make sure there's nothing conflicting with it, and make sure that you actually have that value to give me before I'm going to hand over the sandwich or the car or whatever it is you're buying from me. The bank still controls expansion. We haven't explained that yet. And the bank has the ability to publish different logs to different people. So it could confuse people, it could trick people by doing that. So we want to prevent that. So the next step is to decentralize this transaction log and remove our reliance on the central bank. So to explain how that works, first we need to be a bit more concrete about the transaction format. Each of these transactions, which I've been drawing before as a little orange blob with arrows to the outputs that it claims, is actually just a data structure. The inputs are all pointing to another transaction, and they're pointing to a specific output in that transaction. If we assume that each transaction has an identifying string of some sort that's unique and secure identifier, then the output within that transaction is just an integer. It's just referencing some part of this vector of outputs in the previous transaction. Those inputs also need a signature because you have to prove that you have control over that previous output. You have to prove that you own that key and not somebody else. So each input also carries with it a signature that matches that other key. And then there's a vector of outputs. Each output is identifying the public key that will be allowed to claim this particular output, and it has a value denominated in bitcoins. This entire data structure can be expressed as a string. You just serialize it. You then hash that. You wind up with an identifier, which is the output of the hash function. That's the label that we put on this transaction. So this is transaction GHI because that was the hash of the contents of it. Identify by hash gives you this nice property if you're using a good hash function. The identifiers are long enough that it's unforgeable. You can't come up with a different transaction that would yield the same transaction ID. So other transactions can reference this one and be sure that they're pointing to the contents that they intended to. So this gives you a DAG of transactions. Each one of these transactions points off to the previous one. Because each one contains a hash of the previous one, you can't get any cycles. That would be equivalent to having a collision in the hash. So our goal here is to have users agree on the current transaction graph. In particular, we want to avoid disagreements about which outputs have been consumed, because that would allow double spends. Next step, we take all of these transactions and we aggregate them together into blocks. On a periodic basis, say every 10 minutes, you take all of the current valid transactions and you bundle their serialized form together into a block. The rule is these blocks are building on top of each other. Each block is only allowed to reference is only allowed to contain valid transactions. We don't allow any invalid ones into them. And they're only allowed to reference outputs from previous blocks. So the blocks form a kind of linear history through time. Each block is a lot like the page of the ledger book. If you imagine that users are delivering these transaction messages to the bank on Post-it notes, then the bank is taking all of the loose ones that they have, and every 10 minutes they stick them all into a single page of the ledger. And they fold that, and they paste it down, they don't change that anymore. So the idea here is that we're creating an immutable append-only series of blocks. Each block contains transactions. It's just like making an immutable append-only physical ledger book with a bunch of pages. The next step is that we start looking at the block chain, a series of blocks. Each block is just a series of a collection of serialized transactions. They're just strings. And there's a little header right there. So again, we can serialize that whole data structure and hash it to come up with a block identifier that has the same cryptographic properties. Each header includes a copy of the previous block's identifier. And because that's a cryptographic hash, this means all of the blocks form together into a strong chain. If we can agree on the current block ID, then that means we also agree on the full contents of the previous block, and the block before that, and the block before that. And that means we agree on the contents of the transactions in all of those blocks. So this reduces the problem of agreeing on what constitutes the right history down into agreeing upon a single string, a single SHA-256 hash. And it's computationally impossible to insert or remove a transaction that's already in the log, since that would change the hashes. So what we have so far is a broadcast channel of loose transactions and bound blocks. Everybody is subscribing to this thing. They're hearing about the loose transactions that show up, and they're hearing about the bound blocks that show up. Everybody is validating all of these transactions within these blocks. They can tell whether they like that transaction, that block, or not, whether it follows the rules that they believe in. All of the nodes are maintaining a copy of this blockchain. They're following this history, and so any node can say, hey, that's an unspent transaction, or that's a double spent. All of the transactions that are in the chain are valid, and they're all mutually consistent. There are no double spends within that chain that conflict with each other. We still haven't talked about how to agree upon that block ID, how to keep the broadcast in sync, and how to control expansion. Those are like the three items that we still have left to cover. So we're like halfway there, maybe 70% of the way to what Bitcoin actually does. So why do we actually need to agree on the current block? Why does that really matter? We need this in order to prevent this double spend attack. For an attacker to successfully accomplish a double spend, they need each of their recipients, each of their victims in this case, to see a different blockchain. What they're trying to do is to get those two victims to accept mutually conflicting transactions. One of them says, I'm taking this coin and I'm giving it to Alice. The other one says, I'm taking that same coin and I'm giving this to Bob. If Alice accepts that and Bob accepts that, then the attacker wins. So the attacker needs to take delivery of whatever it is they're buying before one of the victims finds out about the other one. So they need to kind of keep them separated in two separate worlds long enough for them to pull off the attack. So what we really want here is for some means for Alice and Bob to decide upon which of these chains is the correct one. Something that they can use to converge on a single history. If we have a centralized bank, then it's easy. Everybody just pays attention to what the bank is. But the goal here is to decentralize this stuff. So to agree on which block is current, we want to imagine a voting protocol of some sort. Everybody is performing the same computation and using the same input data. And if they accept each other, they'll accept each other's results if and only if the result of that computation matches. So this is where it starts getting clever. In the header of the blocks, in addition to all this other metadata and a reference to what the transactions are, there is a counter. And it's a big field. I think it's 32 bits, maybe 64. And it doesn't matter what the value is. The rule, so block ID is the hash of the contents of this thing. We're using SHA-256. So that means the block ID is a 256-bit number. You can think of it as a string, or you can think of it as an integer. And the rule is we require the block ID as a number to be close to 0. As you know, a strong cryptographic hash is collision resistant. It should be computationally impossible to come up with a specific output value. What we're talking about here is a partial hash collision. We're saying that it's difficult but not impossible to come up with not a specific value but with a range of values. If it's a 256-bit hash and we say, I want the first 4 bits to be 0, then on average you're going to have to do about 16 hashes in order to come up with one, because the output of the hash function for different inputs is effectively random. So what we're using here is, this is a proof of work function. We're saying, I want you to come up with a counter value such that the hash of this block comes out to somewhere in this range. And the range is controlled by something called a difficulty factor that changes over time, but that effectively specifies how much work you have to do in order to get lucky and in order to find a hash that falls into this range. This is trivial to verify. That's the important feature of the proof of work function, is that it's difficult to come up with an answer for it, but everybody else, it's trivial, low cost for them to verify that that answer is valid. And it requires a predictable amount of work. We can say up front how many hashes you're going to have to do in order to have a 50-50 chance of coming up with something that meets this requirement. In Bitcoin, the current difficulty factor as of yesterday is about 1.7 million. That translates into 7.3 petahashes per block. There are currently maybe on the order of 20,000 GPUs all around the world working on a problem just like this. And on average, one of them comes up with a successful answer about once every 10 minutes. So that's kind of the periodic feature here, is the rate at which people find this. This process is called mining. It's something you just keep trying, and every once in a while you get lucky. Now, miners, so the machines that are doing this, they're trying to find partial hash collision, they're called miners. Miners are working on a block that is based on, it's sitting on top of some previous block. Because this header has a pointer to the previous block in it, they have to choose what they're going to work on top of. The rule is that miners will work on top of the valid blockchain that represents the most cumulative work. So for it to be a valid blockchain, every transaction in it has to be valid. There have to be no double spends, and all of the rules of the economy are being followed. So whatever the rules are about expansion, about how transfers work, those all have to be followed in order for a miner to be willing to put work on top of it. Bitcoin miners spend all day long incrementing the counter and recomputing this hash until they find something that matches the difficulty factor. What they're trying to do is to find that partial collision and extend the longest chain by one more block. So Alice here is trying to decide, should I work on top of block 4A or on top of block 3B? She always works on 4A because that has a longer chain. It has more cumulative work. More hashes have gone into it. The current blockchain in Bitcoin is about 137,000 blocks long and represents about 52 exahashes of work. There's 10 to the 18. And that represents work over the last 2 or 3 years of Bitcoin. This is useful because it lets us resolve races and disputes in a decentralized fashion. Eventually, one chain will win. To see why, imagine you have a large group of miners working on a new block. Everybody's trying to come up with block 3. A race occurs when 2 miners find a block at the same time, or at least outside of each other's light cones. The definition of simultaneous depends upon how quickly information can travel. If I find a block before you do, if I find a block before I hear about the block that you found, then that counts. Both of us think we have found the first one. Block discovery is a Poisson process parameterized by the number of hashes per second being generated. So the chances of an accidental race are fairly low, and they're linear in the diameter of the network. The faster we can move information across, the faster we can flood the discovery of the new block out, the lower the chance of a collision space. So what happens is some folks hear about the one block first, some other folks hear about the other block first, and that splits the world into these 2 cliques. Some of them are working on top of 3A, some are working on top of 3B. Eventually, somebody will find the next block. The larger clique has a better chance, but it doesn't actually matter. The chances of hitting a simultaneous discovery twice in a row are even lower. They're exponentially lower than finding someone. Once that person down on 4B finds their block, they broadcast it out to the network. because that new chain is longer than the old one, as soon as people hear about the new block, they'll abandon the old one and switch over to it. All the people in the bottom are now working on top of 4 instead of on top of 3B because it's the longest one they know about. Even the miners who are working on the competing block will give that one up as soon as they hear about the longer chain. So now you have all, or at least most of the miners working on the same thing. Over time, the vestigial chain is abandoned and forgotten as everybody piles on to the new longest chain. And so much work accumulates on the real chain, on the longest one, that the alternatives can never catch up. So this is this really interesting decentralized converging on a particular outcome based upon how much work is going into it. The fact that it takes a lot of work in order to come up with an alternate chain also helps protect us against double spending attacks with an economic argument. So remember that to pull off a double spend attack, the attacker has to present multiple distinct valid blockchains to the different victims. It has to convince them that this is the truth for you and this is the truth for you, and you can benefit from the fact that those truths are really conflicting. This becomes impossibly hard when the majority of the miners are working on the real chain. If the attacker here is trying to come up with an alternate all by themselves, the amount of hash power that they have, the amount of CPU power they have, is so much smaller than the rest of the world that it's going to be infeasible for them to come up with an alternative, at least prohibitively expensive. And as we'll see later, that's enough. So to maintain integrity of the transaction log, we need lots of people to mine and spend lots of CPU cycles. But that costs real-world electricity. That costs actual dollars to do that work. So we have to do something to give them incentive. And by the way, we haven't yet explained where bitcoins come from in the first place. We need some way of creating them, and we need some reasonably fair way of distributing them. There's an economic argument that says it doesn't actually have to be a fair distribution. It would work just as well in the long run if one person got all of the coins in the world and gave it out to their buddies. The Koch theorem talks about that. But there's a psychological argument that trumps that says nobody's going to use a system that feels unfair. So one of the goals of the Bitcoin system is to find as fair a possible way of distributing the initial creation point. So the only thing that we have to offer is Bitcoins, and we need people to do this work. So maybe these are related, and we should pay miners with Bitcoins. The way this works is that each block is allowed to have a single transaction in it called a Coinbase. This one has 0 inputs and 1 output, and provides a fixed specific quantity of Bitcoin, a certain number of credits. And this is a reward for finding the block. Currently, this is providing 50 Bitcoins per block. So in exchange for doing a predictable number of hashes, a certain number of CPU cycles, a certain number of joules of energy, a certain number of dollars spent, miners get, on average, 50 Bitcoins out of this. This is their reward. This is why they put all the electricity into this stuff. A rational participant is going to compare the expected future value of those 50 Bitcoins. They're going to try and guess how much that's going to be worth to them in units of whatever they care about in the future. And they're going to compare that against how much they know it's going to cost them right now in order to do enough hash work in order to get that block. And they compare those two, and they either run their miner or they don't. This is allowing the market to take place here, where people can decide how much this is worth it to them. So miners are incentivized to enforce the rules of the economy. The reward that they get, that reward transaction, is contingent upon other miners agreeing with their decisions. If they do something wrong, if they allow in a bad transaction, if they try and claim a bigger reward than the rules allow, then other miners will ignore that block. They'll just keep on working on what they think is the valid blockchain that doesn't include their stuff, because it's not valid. So that means the reward transaction won't be in the future blockchain later on that everybody else recognizes, so they won't be able to spend it. So it means they have to be they're going to be very careful about the transactions that they put into those blocks. And they're going to follow those rules very strictly themselves, because any violation costs them the reward, and it wastes all of that work, all that CPU time they put into it. So miners are effectively betting their CPU cycles on an outcome that other miners will accept the decision that they made. The payoff is in BTC, in that reward. And they can maximize their chances of winning this bet by following all of the rules. There's a lot of really interesting game theory going on here. If you try and break the rules, you get ignored and you lose out. You spend something, you don't get anything in return. If you follow the same rules as everybody else, then you get a reward. The payoff is better when you cooperate. And there's some really clever incentives that kind of drive these things together. That is one of the reasons I'm so impressed by the Bitcoin design. So you do integrity protection work, you get paid. if you do it wrong, either accidentally or because you're trying to cheat, then you've wasted CPU cycles and not gotten anything for it. Potential attackers are incentivized to follow the rules as well. If I've got a whole bunch of mining capacity and I'm trying to decide as an attacker, as a rational attacker, whether I'm going to try and make an alternate history so that I can pull off a double spend attack, or whether I'm going to mine normally and get the reward that I get from mining normally, then I have to compare those costs. The chance of me succeeding in a double spend attack times whatever payoff I can get from it, I'm going to compare against money I could get by being honest and following along. And in general, given that there's so much hash power feeding into this, so many people are working on this right now, almost all miners are actually going to choose to be honest. I mean, all the attackers recognize that they won't do any better by cheating. That's really strong. That's not saying we have to depend upon somebody's behavior because they're incentivized to do the thing we want them to do anyway. This is a lot stronger than most of the security systems that we usually wind up with. It's possible for, if a group can get a lot of computers together and get more than half of the hash power, then they can start making parallel chains that can outstrip the rest of the world. But it's pretty easy to detect because you start seeing conflicting transactions. You start seeing alternate chains that don't die. And if it's a cabal that has a bunch of individual members, then those individual parties may want to defect. They may realize that they can make more money by honestly mining and following the normal rules than by sticking with the cabal and trying to cheat. So I think there's some research to be done here, but I think that those cabals may be unstable. There may be good reasons for the parties in them to fall apart and start disagreeing. And then everybody becomes honest and contributes to the main pattern. The fact that this blockchain, these transactions are embedded in this blockchain, creates an interesting side effect that's fairly unique to Bitcoin. Very few other systems have this. Bitcoin transactions have a certain maturity, and it's a value that improves with age, kind of like wine or cheese or teenagers. The attacker's task of producing a longer blockchain with that alternate history gets significantly harder as time goes by, as more blocks are added on top of the transaction that they're trying to fake. So the recipient can choose between attack resistance and settlement time. If somebody is buying a sandwich from me, then I say, yeah, sure, I'll give that to you right away. If somebody wants to buy a car from me, then I may wait a couple of hours for a lot of blocks to be piled on top of this thing, so that I know that the attacker had that much harder of a job of reversing it, of coming up with that alternate history. So it's a lot like waiting for a check to clear. You know, if you deposit a high-value check in your bank, they're going to tell you to come back a week from now and make sure everything's settled and nobody's trying to roll the thing back. So it's kind of unique in digital currency systems, but it actually parallels what we have expected out of kind of real-world money a lot better. The reward for each block, currently 50 Bitcoins per block, is scheduled to drop at a predictable rate. This is built into the code. In particular, other clients will accept a Coinbase with a generation value that is no larger than this value. If you try and if you change your code to keep generating more than 50 Bitcoins per block after it's supposed to have dropped to the next level, then everybody else will ignore your transactions. As a result, this is specifically every 210,000 blocks the reward drops in half. And because they're supposed to be generated on average every 10 minutes, this means roughly once every 4 years that value drops. As a consequence, the total amount of Bitcoins in existence asymptotically approaches 21 million over time. This is really interesting from kind of an economic money supply point of view. It's fixed and predictable expansion, unlike what you get in any centralized currency where the Federal Reserve can say, you know, we need some more money in the system. We need to affect inflation in some particular way or slow down or speed up the economy. So Bitcoin doesn't have that. The expansion rate eventually hits zero. That removes one of the variables that drives inflation. This is something that some people like as far as not letting individual parties do political shenanigans or whatever, not being able to figure out what to do. But it does raise the interesting question of what incentives do miners have after the reward goes away. You know, in time, the amount of money they get out of each one of those blocks drops off to zero. Why should they bother continuing to mine? So before, I said the transaction rules say that the outputs can't be greater than the inputs, but it doesn't actually require them to be equal. A transaction is said to pay a fee if the outputs sum to a value that's less than the inputs. It's a little bit lossy. I put in 12, I take out 11, there's 1 left over. And that leftover goes to the miner who finds the block. Specifically, the rules of what miners pay attention to, what they're willing to build upon, say that it's valid to have a reward transaction that includes a sum of the fees from all of the transactions in that block. So in this example, the person Alice, who manages to find a hash collision and mine this block, is going to get a reward of 54.1 credits. She gets 50 for the expansion number, and that's the one that drops in half every 4 years. And she gets an extra 4.1 from all of the different transaction fees that are present in all the transactions. In the long run, as the reward drops, as the expansion reward drops, clients will have to provide a fee in order to get their transaction published. Miners will basically ignore any transactions that aren't juicy enough. They'll start with the ones that are the most lucrative and have the higher fees, and they'll probably stop after some number of them. They won't bother with the smaller ones. So as a client, if I'm giving you some Bitcoins because I want to buy something from you, I get to choose between a small fee and fast service. If I give a really big fee on that, then lots of miners are going to work on it. It'll get into the transaction log quickly. I'll be able to get my sandwich or my car from you that much faster. If I don't want to pay those fees, I put a very small fee on there or no fee, and then very few miners are willing to pay attention to it. And then it's a very long time until one of the remaining miners that will pay attention to low fees will get it into the block. In the long run, that lets the market stabilize on an average fee. If miners insist upon charging too much, then they're not, and if there aren't enough transactions that provide that fee, they're not making much money from it, so they'll drop it. If I'm not satisfied with the speed of the service that I'm getting, I have to raise the fee. Those price pressures push against each other, you get a market effect, and that should stabilize on an average fee that covers the miner's expenses and also gives them a reasonable profit. So what we have here is, those are the basics. We have clients broadcasting their signed transactions. We have miners that are collecting all those valid transactions and combining them together into blocks. They do proof of work hashing on the blocks to get a reward paid out in Bitcoin. The proof of work on the blockchain makes it expensive to create lengthy alternate history. So double spends are not economical. It might be possible if you have enough power, but it may cost you more than what you're going to win. The properties we get out of this are consensus-based rule enforcement. It's impossible to steal Bitcoins because the cryptographic signatures are unforgeable. And it's prohibitively expensive to double spend or create extra stuff that falls outside the pool. New Bitcoin that's being created is allocated proportionally to the amount of work being performed. So that feels pretty fair. That's kind of the most fair system you can get out of a decentralized system. The expansion of the Bitcoin supply is predetermined. It's following a curve the regulator recognizes. And no single party can change the rules. Any individual who changes their code to behave differently will get punished by their reward not being recognized. So it requires you to get a majority, and really more than a majority, of people to agree to any changes. If you wanted to change the shape of that curve, if you wanted to change the fee rules, then you'd have to get a lot of people to agree to that. There are a couple of clever tricks kind of in the protocol, and a couple of highlights of those. The difficulty factor automatically adjusts. Every 2016 blocks, which is supposed to be about every 2 weeks, the client looks at the timestamp of the current block and the timestamp of 2016 blocks ago. And ideally, that should be 2 weeks. If it's less than that or more than that, it figures out what the new difficulty factor ought to be by just dividing. It says what difficulty would have been necessary to make that actually take 2 weeks instead of however long it took. And then it says, all right, I'm only going to accept blocks from other people that have that as a difficulty factor. There's an NTP-like protocol in order to deal with clock skew and inaccurate local clocks. But in general, it adjusts itself in order to maintain that rate. This graph here, you can't quite see, but if you follow the slides, you can get it bigger, is a difficulty factor versus time over the last 2 years on a logarithmic scale. So it's been rising exponentially. It's been growing by a factor of 10 about once every 3 months for the better part of a year and a half. There are a couple of spikes in this that correspond to slashdotting, correspond to GPU miners coming online, which were a lot more efficient than CPU miners. Raises the question, why won't this just keep on rising to infinity? And again, there's a market equilibrium that can be established here. Once it becomes too difficult to mine, and the yield you get from it is too low, it's not profitable anymore. So many people will turn off their miners. They say, this electricity isn't worth it for the return I'm getting from it. that means the total hash rate drops. It takes longer to make those 2016 blocks. All of the clients lower the difficulty factor. Now maybe it becomes profitable. People get back in the game. They waddle around that optimum price there. So in the long run, you get an equilibrium point that's driven by how efficiently miners can operate and how much reward they expect to receive. So it factors in kind of the current price here, the expected future value of it. Bitcoin relies upon the unforgeability of 256-bit CBSA signatures and the lack of full print images in SHA-256. It's using the collision-free properties of SHA-256 as a proof of work function, but it could tolerate partial breaks. If somebody discovered how to find a partial collision, you're asking somebody to find an input value such that the output hashes to less than X. If they discovered that twice as fast as you expected them to, then as soon as everybody starts using that technique, the difficulty factor doubles to go and compensate for that, and life moves on. It's really neat how it actually is mostly unaffected by small breaks. And those are the kinds that we've seen in these hash functions. When SHA-1 started having problems with their finding are attacks that make it faster but not infinitely fast to find a collision to find a collision. Will 21 million Bitcoins be enough? That's the cap on how many of they're created. First off, they're actually subdivisible down to 8 orders of magnitude. Internally, all of Bitcoin values are represented with a 64-bit integer, and the UI just divides everything by 10 to the 8 before presenting it. My friend Zuko estimated that if the entire current global economy were translated into Bitcoin, if Bitcoin were the only currency anybody used in the entire world, then the smallest divisible unit of Bitcoin, one of these 10 nanobitcoins, would represent about 1 US penny. So that's about the right order of magnitude to me. But deflation is so interesting. Bitcoin intentionally eschews central control of expansion of the money supply as a financial policy tool to control inflation. The money supply will eventually be fixed, but inflation can still happen just because of expansion of the economy. And deflation could also be interesting as money gets lost over time. If somebody forgets their private key or their computer crashes and they haven't gone back into that key material, those coins are no longer available to anyone ever. And so in the long, long run, the total number of coins in existence can be expected to drop a little bit. So that's kind of still. A couple of practical deployment details. Start off, everybody was using CPUs. The original client had that built in. Some folks worked out that GPUs are more cost effective. It's about a factor of 10 more efficient in terms of hashes per joule than a CPU. So currently everybody are using GPUs. There are folks that are developing FPGAs and using ASICs to do this stuff. The way to think about that is that the cost per hash is following a step function, with each step is a new kind of technology applied to it. So difficulty factor will adjust for that, but it's interesting to see how this is driving technology. And in some ways, Bitcoin is a long-term experiment to build SHA-256 hash crackers. Like if you wanted to find a way to incentivize people to go and put a lot of effort into making hardware to do it, it's a great way to do it. A cheap GPU, something that it fries for $100, can do about 150 megahashes per second, and it burns about 100 watts. At the current difficulty factor, that represents an average of 1 block every 17 months. And that's the Poisson process. That's, it might be a month from now, it might be 5 years from now before you find something. That kind of return is really uneven, and that's not very easy to work with. Even the fastest GPUs only manage to get a block about once every 2 or 3 months. So a mining pool provides much more uniform results. This is a website where everybody is working on the same problem, they're all working on the same block. The reward for the block goes to the operators of the pool, and then the operators of the pool dole out little pieces of that to all contributors according to how much they can pay. Almost everybody, lots of people are using these right now. The 3 largest pools that are out there, there are about a dozen, maybe 20 pools operating. The 3 largest ones collectively provide about 75% of the total hashing power. There are some tools here you can follow. There's a yield calculator that says if I have a GPU that can do X many hashes per second, then how many Bitcoins per day does that represent? There are exchanges where you can buy and sell Bitcoins for dollars or euros or other currencies. Mt. Gox is the largest one out there. It's currently moving about $500,000 per day. And they had some well-publicized security problems a couple of weeks ago, and they're kind of still recovering from that. And there are a couple of tools here to show you what the blockchain looks like. That we look at current exchange rates, what the difficulty factor is, hash rates, and stuff like that. There are about 7 million Bitcoins in existence right now. on that expansion curve, we're at that dot. We're only about a third of the way there. There are currently about 400 transactions per hour crossing through the network. The difficulty factor is at 1.7 million. It's like I said, been raising by a factor of 10 every 3 months, but it's starting to flatten out. People are starting to decide it's not quite worth it anymore. Currently, the network represents on the order of 14 terahashes per second, and that represents about 20,000 GPUs. The total, that's probably about 7 megawatts of power being spread out over all the world where people are playing around with stuff. The blockchain represents about 83 quintillion hashes right now, 83 exahashes. A high-end HD 6990 GPU currently yields about half a Bitcoin per day. That represents about $6 or $7 per day and burns about 10 kilowatts. So you have to compare how much you spend on that versus how much you think you're going to yield on it. And the current price is about $14 per Bitcoin. Client is in C++, using Boost. C++ is not the first language I would choose for a security, financial, critical piece of software that is intentionally exposed to complex network packets coming from anonymous senders from all over the internet. But it actually seems to work pretty well. The code seems pretty clean, pretty thoughtfully laid out. It's using IRC to contact all the other miners, all the other participants that are out there, has an overlay network. Use IRC just to flood out the addresses to let them know where to connect to each other. It's using elliptic curve DSA, using the NIST curves, SHA-256. Is it money? I'm not even going to get into that. That's a very big, complicated topic. But it does behave a lot like money. Is it anonymous? Yeah. So the transaction contents are very, very public. I'll show you in a minute the block explorer, but everything about all the keys, how much value is transferred from one key to another is part of the permanent record that every client out there has a copy of. The source of a transaction, like who created that transaction, the IP address is mostly secret. It's being flooded out to a lot of other machines, so you don't know when you hear a transaction over the wire whether the guy at the other end of the wire created it or whether they're just relaying it for somebody else. And you could always run that over Tor, so that's not a very useful thing. Key ownership is mostly secret unless it's revealed somehow by the sender or the recipient. If I have a certain key and you send money to me, you know about that, and you might tell the world about that, but you might not bother telling the world about that. If I have two separate keys and I make a transaction that combines their value to send off to somebody else, then it becomes obvious to the rest of the world that those two keys are related, that you can trace things back that way. It's surprisingly similar to cash, given that the dollar bills have serial numbers on them. If you were to imagine that ATM machines read the serial number off of every bill as they handed it out and remembered that it was Brian that was through that money. And if the corner store wrote down the serial number when I buy a sandwich from them and they told each other about that, then you could trace cash as well. But in general, they don't, and it's a big hassle to do so. So that's why we think of cash as being kind of untraceable. So it's roughly on that same level. It's the kind of thing that I won't really claim that it's anonymous, because a lot of the digital currency systems people have built before really were more so. The anonymity set was much larger and didn't have this kind of traceability. But it's considerably more anonymous than using a credit card to get something. There's not a central bank that has a strong real-world identity tied to it. So that's kind of up in the air. In the long run, people are concerned about how it's going to scale. Storing this blockchain, which is just growing and growing. It's currently a couple megabytes, maybe 10 megabytes, but it's just continually getting bigger. How to keep track of all the unspent transactions, how to transfer all this data around, how much bandwidth is being spent on that. People are concerned about the environmental impact of how much power is being fed into mining, how that's going to grow. There have been DOS attacks against miners, against pools. There are exchanges that have been DOSing each other, trying to prevent people from exchanging money. There's questions about price stability that's been fluctuating a lot. There are legal attacks. People are still trying to work out how to manage these keys securely. Some people are working on dedicated hardware, iPhone apps, offline systems that aren't quite so vulnerable. How to make this really usable. Botnets are kind of a problem, but not really. If they're not too big, then it feels unfair and people are stealing money, but it's still contributing to the stability of the overall network. And you might just think of that as another step on the CPU, GPU, botnet, FPGA, ASIC And botnet operators have costs too. You know, it's conceivable that this is a better use of botnet time than sending out spam, and maybe that's a good thing for the world. Large botnets are kind of unlikely, but the amount of hash power involved is such that it would be hard to get a supermajority. And it's a risky thing to run on your botnet because you're using up the target computer's CPU. And a hot CPU is much more obvious. Part of the economics of botnets are that you pay for how much of the botnet is left over when you've finished using it for whatever your malicious purposes. And so if you cause damage to the botnet by virtue of doing something that gets your network discovered, then that costs you as the consumer of the botnet. So that's kind of a problem. We've got bonus slides, but I think I'll hold them off for later. There's some extra stuff in the deck if you want to take a look at later. So thank you much. Any questions? I know, it's a lot of information, kind of overwhelming. In general, I found it's a really cleverly put together protocol. I've been very impressed by the way the incentives are balanced and how all of the concerns I came up with as I was reading through it got answered somewhere else. Yeah.
So is it Mt. Gox?
I think I've seen them
The
pronounce
Mt.
it.
Gox incident's worth getting into.
Yeah.
There's a compromise to the DIN account.
Yeah, so Mt. Gox was compromised. I don't know the full details of it. Mt. Gox it started out as Magic the Gathering online exchange is where the domain name comes from. And it's an exchange. You set up an account there. You send them some dollars. You send them some bitcoins. You push buttons to trade. You know, it just looks like it's like a E-Trade or something. They got compromised. The story that I heard was that there was some sort of auditing relationship they had. Like they licensed the code from somebody or they purchased the site from somebody, and the owner, the party they purchased it from, retained the right to make sure they were doing something a certain way. Like that they were paying them the right fee, so they wanted to know their total transaction volume or something. And so that party had read-only access to the database. And that party's computer got compromised in some fashion. And so the attacker got access to the database. And they used that to, it was kind of standard, website compromise in that somebody got access to enough information to brute force some passwords on some high-value accounts. And then they used that. The site had a withdrawal limit, so you couldn't withdraw more than $1,000 per day or $1,000 worth of bitcoins per day. Bitcoins are irreversible once you send them somewhere. So the story that I heard was that the attacker found a high-value account. They sold all of the bitcoins in it, which was larger than the total market float. So it crashed the entire market down to zero, which then allowed them to withdraw more bitcoins than they would have because the price of the bitcoins was lower than people started with. It was something really low. There was some other limit there. It sounds like they didn't actually get away with more than a couple $1,000s, but part of the attack was there specifically to try and get away with even more.
Yeah, there were rumors of sock puppetry and so on, trolling or orcs.
Yeah.
To create a greater panic.
Yeah.
Because the price went from $7.50 down to a penny.
Right, yeah. They're trying to create a panic and selling, from what I heard, it was basically one large account that had so many coins in it that selling everything in there at market erased the entire market. And so what they ended up doing was rewinding the clock, like what happens on NASDAQ every once in a while, and starting over again about 2 weeks later. But it got a lot of people scared because what they're recognizing is that having absolute currency schemes in which transactions are irreversible is great for a number of purposes. From a merchant's point of view, it's great to not have to worry about rollbacks, and it means all your fees can be much lower. But it also means that many of the features you want out of a bank, like somebody who will make a decision to give you back your money if somebody else made a decision you disagree with, are still valuable. And so I think in some ways the Bitcoin world is following an education curve that the real world economy has already traversed over the past 500 years. And have many of the same lessons.
Is the curve going up or down?
It's not clear whether that curve is going up or down.
So the interesting thing to know, I think, is that although the system is designed so that transactions cannot be falsified, it does not mean that naughty things can't happen. The attacks are made before transactions happen. So in the case of Mt. Gox, those things had not been turned into blocks yet. And so what they were doing was fiddling the ledger basically inside of Mt. Gox before they become actual Bitcoin transactions.
Yeah.
And the other attack that I think that has happened is where people use botnets and other things to get into people's key file on their machine and then use those keys to spend the money.
Yeah, Dan's pointing out that a lot of the attacks happen kind of before the protocol actually kicks in. And
Lock one door, but there's still there's other ways to get in.
Yeah, there are lots of other doors. And I think one thing that, one hope I have is that the popularity of something like Bitcoin will encourage people to take securing their personal machines more seriously. Like there's actual money involved here. And it's not something where they can rely upon their credit card company and telling them, hey, somebody figured out my credit card number and got this stuff from me, please give it back. It's much more absolutist like that. There are Windows Trojans out there that specifically look for the private key wallet file and send them off to an FTP site of some sort. There are other forms of malware that are trying to attack that. I haven't heard of anything looking at the network protocol yet. The implementation was pretty solid, but it's worth investigating.
There are already people building traditional ledger systems on top of Bitcoin, like mybitcoin.com and instalewallet.com. They're just sites you can log in, you have a Bitcoin account there, and they keep your money for you. You can transfer it out.
Yeah, there are ledger systems on top of Bitcoin, and yeah, as Zen points out, Mt. Gox is effectively one of those, where Bitcoin is the backing currency, and there are other sub-currencies that you trade with, and it's only when you extract it out of that system that it becomes as real as Bitcoin is, which is exactly what the real world money system is as well. There's this thing called M1, which is the money that the Fed gives out, and there are M2s and 3s and derivatives that banks, that kind of thing. Yeah.
What does the government think about Bitcoin?
The government is mostly unaware. There were repair senators that said, oh my God, there's this horrible thing called Digital Silk Road. Sorry,
You can buy drugs with Bitcoins.
Yeah. Did they actually call it Digital Silk Road?
Yes.
Okay. Which is unfortunate because there's another very interesting thing called Digital Silk Road.
Well, it was Silk Road something.
Silk Road. It was just Silk Road, right? Some online site where you can buy drugs with Bitcoins. And it was like you connect to a Tor hidden server, you tell them an address to mail an envelope to, and you send in Bitcoins. And they said, oh, this is horrible, we have to stop this. And they mentioned Bitcoin in the process of describing this thing.
This stuff happened with $1 million too.
Yeah, this is happening with other virtual currencies.
Happens with US dollars also.
Yeah, and I mean, all of the centralized virtual currencies end up dealing with this sooner or later. It's kind of a seasonal thing. A law enforcement or concern about gambling or concern about other forms of smuggling, whatever, kind of comes and goes. A lot of those online systems have to be careful to make it not look like a currency in order to avoid that kind of attention. Either they make it really hard to get dollars out of the system, or they make it really hard to transfer from one party to another, or they make it really hard to build gambling machines in the game. Like there was a time when I think Second Life had removed the random number generator from their scripting language in order to make it not look like you could gamble with the dollar. Yeah.
What's your prediction? Where do you think the Bitcoin project will be in, let's say, 5 years?
I'm giving it 50-50 odds of continuing to be successful or exploding catastrophically. I think there's a good chance that there will be some catastrophe, that there will be some protocol flaw or some implementation flaw, or the way that people use it, there will be something drastic there. And it may explode messily, and people will lose the value that if they're using it as a speculation currency and they think that's fun, then they'll lose what they speculate on that. But I think it's tremendously educational. I think that whatever follows on Bitcoin is going to be spectacular, because we're learning a lot, both in terms of how to build the protocols, how to make this stuff usable, how to make it scalable, how to get the clients to be usable. We're learning a tremendous amount from it. And it's inspiring a lot of people to recognize what you can do once you can hack on the currency exchange, just like you can hack on protocols and data exchange. All right. Thank you all very much. Oh, yep.
So you skipped over money.
Money, yeah. So I think money is a tool humans have invented in order to facilitate transfer across time or geographical distance or cultural distance. It's something that two parties believe has some value and they're willing to use as a trade. It needs to have certain properties to be useful, like unforgeability, mostly unforgeable, mostly secure in those senses. So in that sense, it provides all of those same properties.
There's a different point of view. Augusto Graziani is a non-conforming economist who put this forward. Steve Keen is currently active. He's an Australian economist. Graziani's model is it's not like Carter. There aren't two parties, there's three parties. It all is a bank. And the bank has two important functions. One of them is just search. Because, Farmer Maria and Plumber Joe can't find each other to swap their pigs and their copper pipes. So money helps, and banks help people exchange that way. But the more important function is that the bank clears the transaction. And so when you exchange money, like you write a check, you're no longer indebted for buying pigs or pipe. You're now actually...
You're trying to create an abstraction boundary.
And you're also making something that the bank can do uniquely, which is lend. You can create money. And that's not true of Bitcoin.
That is not true of Bitcoin. It could be true of a derivative thereof. You could say Bitcoin is a backing currency. If there's a given party that has a certain quantity of Bitcoin, then I'm willing to accept something else, lender coin, something like that, which is backed partially by it, some sort of fractional reserve scheme. And people would have to accept value or not in that secondary currency according to what they thought of the provider and the redeemer.
So just to point out, I think the reason money is interesting, it's not necessarily a good thing, is that it is credit in modern things. It is completely created ahead of any fractional reservation process. There's M1, that's all garbage. Sorry.
Yeah. Oh yeah.
Banks lend promiscuously, and then they struggle to meet their reserve requirements and get exemption in other issues of Federal Reserve. So that's an interesting angle to our modern world. It's caused great, collapses as well as booms.
Yeah.
Seems like Bitcoin lacks that, which could actually, you could think that would be just good, but it could also harm its uptake.
Yeah, I mean, there's a lot of, it's not providing a lot of features we've gotten used to. And there are some people that think those are unequivocally bad features. There are a lot of good reasons why they're there. Yeah, so it feels to me like it's going to be a tool that other stuff can be built upon. There are already a couple of other derivatives of this. There's a project called Namecoin, which is using the same Bitcoin blockchain hash mechanism, and instead of allocating out just kind of virtual units of currency that you use however you see fit, it's allocating name to IP address allocations. And so it's like DNS, but you have to pay for the registrations and pay for their renewals in terms of the coins of the system. And you do hashing work in order to get those coins. And so the folks that are running that one are hoping to, I think their long-term dream is to someday buy a top-level TLD and say that name.bit is controlled by the Namecoin machine. And there's a certain set of economics according to control how you go and get those. And the most valuable, cool names are the most expensive, and there are ways to trade them. But it's not something that ICANN can go and control, or those domain names can't be seized because it's being allocated according to the same sort of algorithms that Bitcoin is doing. And so if people are already thinking about derivative currencies or things that are like currencies, things that have value and can be traded in a fungible in some way, based on this. It's inspiring a lot of people to think about things differently.
Somebody's already built a stock market.
Yeah, there's a stock market. There's a lot of trading stuff. There are tools.
Assassination markets?
God, I hope not. So yeah, this is people are building kind of standard financial tools, things to look at the price of Bitcoin over time with all kinds of crazy technical analysis that makes no sense to me at all. So yeah, there's a lot of interesting stuff there. The Block Explorer is a way of finding out all the transactions that appeared recently. A lot of tools to go and look at value over time, things like that. So, cool. Thank you all very much.